you. Yeah, I'd say that actually my liaison with the Technion started much earlier. When I was in primary school, I actually attended courses here for children learning to program in Algol W. And we were fitting punch cards to a Boros machine, and later there was an IBM 360, which was later replaced with 370. So lots of IBM equipment was here around. So it's a longer liaison that you can think, but now I have a second marriage, and it's a younger one. So I was asked to talk about network science. So what is the idea of network science? Well, apparently networks appear in in many diverse fields of science. So we're looking at biology, in geography, in engineering, in physics, social sciences, of course. Here you see two examples: the internet connectivity map, the airport connectivity map. This is a business relationship between companies. So we're looking at economics. So these are biotech industry in the US in '88, with the relationship between companies. And then if you go a few years ahead, you see that it become richer. You can look, of course, in biology, there's multiple networks that people are studying. And this is just an example of a gene network of a human versus a fly. So it's really everywhere. Oh, of course, the last one is social science. Social science were one of the first to look at networks. The example here is the relationship between the terrorists of the 9/11 plot, where the color coding is by the flight, and the gray ones are collaborators which did not took the flights. And you can see here in the middle, what should I press? This is Muhammad Atta, who was the leader of this group, and you can see how central he is to the network. Of course, nowadays when we look at social network, we can use a huge network like the Facebook network, the Twitter network. I just recently obtained a network of gamers that we crawl in a few weeks, and it has 9 million nodes and 300 million or so edges. So when we look at social networks, these are really huge graphs. So many people in different diverse areas look at network, and the idea is that we can share a lot. We can share ideas, we can share tools. And interestingly, in some cases, the problems are really, really ubiquitous. We're all looking at the same thing. We look at centrality in networks, we look at clustering, and in this case, sharing tools is easy. And a lot of great ideas come up in different disciplines. Sometimes you do need to have adaptations for the tools because each field has its own thing. And in some cases, the problems are really domain specific. And there's a whole spectrum of how unique a problem is to its field. So the whole idea of network science is let's talk to each other, share ideas, share tools, and learn. And hopefully it will expedite the rate at which research is flowing. So what I'm going to present today is a case study. It's nice because it's a really small, well-defined problem that can be easily explained. This is the case of studying graphlets and motifs. So what is a graphlet? So we look at a huge complex network, and you can find there many small graphs that appear in the network. For example, there's a triangle here, and a square, and this small graphlet. And you can ask yourself, how many of these appear in your large network? So why it is important? Actually, why just only these three I showed you before? Maybe I want to count all these ones and ask how many of all these 3 and 4 type graphlets appear in my network. And a graphlet is just a small subgraph. It's a short way to say a small subgraph. So why is it important? So it all started in 2002 in a lab in the Weizmann Institute. Uri Alon, who is a physicist that did the transition to system biology, looked at various biological and also other networks, and he noticed that some small graphlets appear more often than others. So he starts thinking that maybe it tells us something. So if a small graphlet appears much more than you expect it to appear, it tells us something about the way the network operates. So he was looking at directed networks. In these networks, so if X points to Y, it depends what the network is. For example, if it's a gene regulatory network, it means that gene X regulates gene Y. If it's a neuron network, it means that the neuron X feeds neuron Y. If it's an ecological food web network, it means that animal X is eating animal Y. Yeah, so there are various ways to describe all sorts of activities as directed networks. And he was looking at all the possible directed graphlets. And here you see all the ones that have 3 nodes. And what he was doing, he was generating random networks with the same degree distribution as the network it has. And he counted the number of all these motifs in these networks. And if he showed that one motif or several motifs have much higher, you can count a much higher count than in the randomized network, he would say, oh, this is interesting. Let's see what does it tell us. And if you do the work, for example, if you look at the gene regulatory network, look at this motif. It's what you call feed forward. So X regulates Y and Z, and Y also regulates Z. And for Z to be activated, it needs that both X and Y are going to be active. So in the E. coli network, for example, you have 40 times this motif. But if you randomize, you see that the average is only 7 with a standard deviation of 3. So 40 is 10 times 10 standard deviation far away from 7. So it has to have a meaning. So this is what you call a z-score. This is the number of appearances in the real network minus the number of appearances in the randomized networks divided by the standard deviation. So why is this so important for the E. coli? And it's not only E. coli, it's this other organism as well. So if you think about a gene regulatory network, if you have, so you can think of it as what we do in control theory. Yeah, we do impulse response. Yeah? So you give it a small impulse, a short impulse. So X gonna, since it regulates Y, it's gonna start increasing Y activity. But since it's very short, Y would not rise to the level it can start regulating Z. So Z would not react. Only if the impulse is large enough, Y will rise to the right level and Z start being active. So this is not a coincidence. This is a very good way to clean up noisy short signals. And indeed, it appears a lot in regulatory networks. So I was thinking, oh, this is really great. Let's try to do this in networking. And I was trying to use his program for my AS graph that in 2004 was something like 68,000 edges. It was 25,000 nodes, and it wouldn't go. Just this program was too naive in the way it calculated to be able to do anything. But this is where I could use it. So what you see here is an IP interface graph. So this is what you do when you run a bunch of trace routes. Basically, you look at many, many routes going through a single provider network. And every dot here is an interface, and they are connected with this mesh of directed edges. And you can break these networks in a way that will be small enough for Uri Alon's program to chew. So you do this, and we took 3 different ASs. And this is the z-score of different motifs And look at this guy. This is the bipartite. Yeah, it's what Uri Alon called a bifan. And the z-score is just unbelievable high. So we're talking about 300 standard deviation away from a randomized network. This cannot be a coincidence. Yeah. So actually, if you look at this motif, it's actually a bifan with an additional edge. So it's even higher than you would. So the idea is that if you take this network and move things around, you'll see a lot of bifan. Why do you have this in a IP interface graph crawling? So suppose we have a POP. A POP is a bunch of routers in the same location that are serving a metropolitan area, and this is how it is structured in a very naive way, and I run a lot of trace route through this small POP. Look what I get. I get lots of bipartite. But this is great, because now what I can do is I can start looking for these small bipartites, combine it together, and get these large bipartites, and this will enable me to identify POPs. So I can take this very messy picture of an ISP and eventually get a picture like this. So this is where the POPs are, and this is how they are interconnected. This is a very old picture from 2008. Now we know how to do it much better. So this is nice, but Motifs took off. So they started from biology, and many people in bioinformatics start looking at what can you do with Motifs. So one of the ideas that Uri Alon had is said, look, we can count all the different motifs, all the different graphlets of a network, and compare different networks. And if they have the same motif structure, it means that they operate in the same way. So you can classify networks according to their operation, which is really nice. But then other people took it even further and say, let's look at a single network and count how many motifs touches each node. And not only how many motifs touch each node, but in which role in the motif the node operates. So, for example, if you look at the star motif, does the node always in the center of the star or at the edge of the star? So if you do this, you can now start classifying the nodes in the network and identify different roles that they have in the network. So this is really cool, and I said, okay, we have to do this for the AS network. And maybe we can classify it. However, our graphs are larger. And as we move to analyzing social networks, they're going to grow much larger. The simple algorithm for counting motifs do not scale, because if the motif has k nodes, or a graphlet has k nodes, you need, if you're really naive, you'll need order of n to the power of k, and it's just non-doable if the network grows. So people start looking at two approaches. One is to start thinking of clever algorithms for finding small graphlets. And the other one was, oh, maybe we can approximate somehow the count. And since this work was done by people in physics, many of the work had no formal proof of the complexity of these algorithms, so it was just, trust me, it works fast. So I started looking at this, and we did several things. First of all, we were really the first to suggest very efficient counting algorithm for all the motifs of size 3 and 4. Actually, the first paper we did here was this one, but then later we significantly improved it. In fact, these algorithms are so fast that it's not only that they beat all the exact counting algorithms, they also beat all the approximation algorithms that exist. So we're doing exact counting faster than people approximate motifs, but only of size 3 and 4. Then we can approximate the counting of motifs that are larger up to logarithmic size of the network, still with reasonable accuracy. And this is based on an old work by another Alon. This is Noga Alon from Tel Aviv. And these are Uri Tzvik and Yuster also from Tel Aviv. So this is an old work for detecting basically what they didn't call it graphs, but detecting small graphs in the network. And they didn't realize that they can use the same trick, with a simple tweak, also for counting, not only detecting. So we did this and extended a bit. And then we were also the first to show a sublinear algorithm. This is really interesting because when we look at social networks that are really in the millions of nodes and billions of edges, we want to be able to run sublinearly because even linear, it might be too much. So we were the first to suggest an algorithm to approximate the counting of graphlets in a star, and we showed some lower bounds for triangles and 3 pulses. So I don't think this is the right forum to get into the very details of all these things, but I want to show you a feeling of how come we managed to do things much faster. So this is what we're going to concentrate on. Okay, so to understand this, we need to talk about induced and non-induced subgraphs. So suppose this is my graph. As you can see, it is not connected. It has 2 partitions. And I want to count these 4 motifs. These are the only ones I'm interested in. So when I talk about induced subgraph, induced motif, it means that I take 4 nodes, I take all the edges connecting them, and I ask, what motif do I have? So here, I can take the left partition and see that I have this motif. And then I can look at the right partition, and I have this motif. And I'm done. So this is my count. This is my vector. If I'm interested in non-induced motifs, I can notice that I also have the square, or the 4-node cycle, which appears here. I can just simply ignore some of the edges. So when I'm doing non-induced, it means that I'm looking for a shape, and I don't care if there are other edges. I just ignore them. So I have this square here. I can add it to the count. And then I also have what they call tailed triangle. Yes, it's a triangle with a tail. So here I have one. I have another one, another one, another one. So altogether, I have now 5 tailed triangles, or not only one. So now when I'm counting the number of subgraphs, if I'm interested in induced subgraph, this is what I get as before. But with non-induced, I get this vector. Now, 2 key observations. First, it is much easier to count non-induced motif. And the reason is that if I found a square, I don't have to waste time making sure that all other edges don't exist in the network. So algorithmically, it's much easier. I can make much more efficient algorithms. And the other observation is that if I'm counting all the non-induced graphlets of a certain size, I can very easily translate it to induced motifs. How can this be done? So suppose I'm counting the number of squares. And again, non-induced. So obviously, I'm not going to get any of these motifs, because they don't look like a square. They don't have a square in them. But I will also count all the chordal rings, all the chordal squares, the square with 1 chord, once because I will just ignore this edge. And what happened with a click, with a full graph? So I can eliminate any pair of edges that will leave me with a square. That means that if I have a click in my graph, it will be counted as 3 different squares. So what I need to do, if I want to know how many real induced squares I have, I'll take the non-induced counting of squares. I reduce 3 times the induced counting of clicks. And note that with clicks, induced and non-induced is the same. And I have to reduce all the induced counting of chordal squares. But this is, I don't know this because this is induced, but I can do the same trick and notice that induced chordal square are just counting all the chordal square plus 6 times all the clicks. So I do the arithmetics, and this is the formula I get. And I can do this for all the motifs. So this is in terms of computation, it's order of 1, so it's not a problem. And this is the complexity we get for all the different motifs, non-directed, but again, we can also count even the role of the node, so it's even more detailed than we talked about. And you don't have to worry about this E squared that looks so frightening. We know that for any real network, the number of edges is ordered the number of nodes, so this is basically V squared. And actually, this counting, if D is the degree, if the maximum degree in the graph is less than square root of n, actually I can do this in D square E, or D square n, which is even better than V square. So this is one way to do this. And now what we did is use this to do AS classification. So we take the internet AS graph. This is the graph that shows how the different networks of the internet are connected. And we say, can we tell the role of a network by the vector of graphlets? And indeed, we managed to get the same results as the best previous work we could find that is using a lot of side information. This is a work that takes not only the graph, but also go to other databases and ask queries and do some language processing on the name of the AS and do all sorts of things. So we don't do any of this. We just take the graph, count graphlets, and we get the same results. So it's much easier. The question, of course, is can we do better once we know the directed AS graph? This is with type of relationship, and this is still open because our software still don't support directed motifs. As approximation graphlets, so we can do all the graphlets of up to log n, and the meaning of epsilon and delta is that we get up to a factor of epsilon from the true count with probability that it is 1 minus 2 delta. So, where do we use network motifs? So, it started in biology. From there, it shifted very easily to people that do bioinformatics. Lots of people in physics are doing this. Last year, I saw that the data mining community also start using motifs, and now we also do it in networking. And what next? So I think that doing efficient 5-node graphlets algorithms are very important. This is a lot of work. It's tedious, but I think somebody has to do it. And the next thing is to look at time evolution of motifs. So how do motifs actually form in networks? And this, of course, will be network dependent, but I think it's the next thing to understand network evolution. So summary, well, network motif is only an example, of course. It's a very small example that can show, what people can do. And there are many ideas that cross discipline. But I think that networks are the future in the sense that we tend to describe many fields of science now with networks, and the networks become ever and ever larger. And this causes computer scientists to rethink what we teach our undergrads. I mean, we teach in complexities that, if it's logarithmic, if it's polynomial, it's doable. But frankly, n to the power of 3 in a few million node and few billion edges graph is not really tractable. And we need to really think about complexity again. Maybe MapReduce gonna solve it in a different way, but you cannot always do this. So we need to think of approximation algorithm maybe that are at most linear or n log n or something like this. And the other thing is how to store data in the memory. Once your graphs are so large, paging become crucial. In my lab, we've been able to improve the Dijkstra algorithm by a factor of 5, so by 20%, just by finding a new data structure to store the graph that emphasize locality in memory. And 20% for the extra doesn't sound impressive, but this is because the extra in its nature is not a very local algorithm. When we used it for this data structure for other algorithms that we devised that are local, we got an improvement of 80%, almost doubling the speed just by localizing things in memory. So this is a whole new field that needs to be investigated, and I'm calling everybody to join.